Hello guys, welcome to episode 6 of HaskellRank, a series where I solve programming problems using Haskell. Now before we get into the problem, I'd like to take this opportunity to thank everybody for showing their support. To see more content, kindly subscribe and share. Thank you. So today again I've chosen an advent of code problem. Again, for a similar reason to the last one. I think I did a decent job in the last one, but I still want to continue and I want to basically do another problem on similar lines as the last one in terms of, showcasing the ability to create custom types and then consume them and compose with them in a way appropriate to solving problems. So let's get into this. Uh, your plane lands with plenty of time to spare. The final leg of your journey is a ferry that goes directly to the tropical island where you can finally start your vacation. As you reach the waiting area to board the ferry, you realize you're so early. Nobody else has arrived yet. By modeling the process people use to choose or abandon their seat in the waiting area, you're pretty sure you can predict the best place to sit. You make a quick map of the seat layout, which is your puzzle input. The seat layout fits neatly on a grid. Each position is either floor, an empty seat, or an occupied seat. For example, the initial seat layout might look like this. Okay. So let's. I think this should be a test input. I think I already have this because we already solved this problem before. I think the last time I did it using Ruby. Now, you just need to model the people who will be arriving shortly. Fortunately, people are entirely predictable and always follow a simple set of rules. All decisions are based on the number of occupied seats adjacent to a given seat. One of the 8 positions immediately up, down, left, right, or diagonal from the seat. The following rules are applied to every seat simultaneously. If a seat is empty and there are no occupied seats adjacent to it, the seat becomes occupied. If a seat is occupied and 4 or more seats adjacent to it are also occupied, the seat becomes empty. Otherwise, the seat state does not change. Okay. Floor, represented by a dot, never changes. Seats don't move and nobody sits on the floor. After one round of these rules, every seat in the example layout becomes occupied. Okay. After the second round, the seat with 4 or more occupied adjacent seats become empty again. This process continues for 3 more rounds. At this point, something interesting happens. The chaos stabilizes, and further applications of these rules cause no seats to change state. Once people stop moving around, you count 37 occupied seats. Simulate your seating area by applying the seating rules repeatedly until no seats change. How many seats end up occupied? That's the question. Okay. Now, the one thing I want to highlight is there are a few similarities that I noticed here in this problem to the Conway's game of life problem. If people have solved that before, like there are some similarities in the sense that um, you know and it's a pattern where the state of position on the grid depends on the state of the neighboring cells. That's the pattern which is used in Conway's game of life as well. Right. So the only main critical part, which from a Haskell standpoint is actually pretty straightforward, is the fact that we need to apply the changes simultaneously, which is what that really means is that especially for other languages, and I remember when doing in Ruby, I ran into that issue that you cannot actually apply the changes as per the rules If for instance, if you're trying to try to iteratively solve the, or rather apply the rules, right? You obviously cannot change the state until and unless you apply the rules to all of the seating area, right? And that's what kind of makes a big difference. With something like Haskell, we don't have to worry at all about that because we are dealing with immutable data structures. So that'll make it a lot easy for us to ensure that we compute the changes, and only at the end we so we will always rely on a pre-existing state, and that would no one from based on the application of the rules would then eventually result in a new state. And we will obviously never be in a position where you would ever do any sort of partial application. It doesn't make sense, and also you will never mutate, so your logic will never fail as long as it's right. Okay, so let's first start with maybe trying to model the entities in our problem domain, right? The first thing that I see is uh, the I think what we probably need is a representation of a position, right? Because we are dealing with a sort of like a grid, I think it makes sense for us to use like a two-dimensional array. And so for that purpose, we will definitely need the notion of a position, which maps the row and the column index of that this thing. I think we will definitely need that. For that, uh, we can just define a point, I guess, and then we will say that a point type can be constructed using two integer values, and I'll use these values to represent our row and column. And I think, yeah, I think this should come in useful, right? The thing I see is the concept of a seed, and like it says, yeah, yeah, I mean they're basically state, like that's the state of each position. Let's maybe call it state, I guess. So state can either be floor, or it can be empty, or it can be occupied, right? So these are the three states that we have. Let's derive show. Okay, so these are the three states that I see we have. And so essentially our grid would be a two-dimensional array of positions, and for each of those we will essentially have the state, because each position would either be one of these three, right? I think this should work. I'm calling it a grid for the lack of a better word, but I think that's probably appropriate. The first thing quickly I think we can do easily is parse a state, right? Which takes this time, because of the way the input is structured. Let's say the parse state should basically take a character and then parse that into a state, and so that would become, or that would look like, yeah, so we have either a dot character, we know the dot should be floor, and then we have an L character which should be empty, right? Yeah, it's an empty seat. And we have the pound character which is going to be occupied. Okay, so we've already done that. Another thing that I do noticed here is like from a small optimization perspective, right? it's pretty clear that because we'll have to go figure out all the neighboring cells, and then based on that we'll have to obviously define a logic that based on the neighboring cells, or based on the neighboring cells, when based on their state, sorry, we'll have to basically uh, controls the next state of the current cell, right? So we would definitely be sort of navigating through this grid frequently, doing a lot of lookup. And so for that purpose, I think having a map, where the key would be a point value, and then the value would be perhaps the state, should come in handy, right? We would be, if we had that, uh, we could then easily look up the values, rather than or every time we do the index based lookup, because then we find the row and then the column and things like that. If we looked it up in a map, the lookups would be much faster. But we'll get to that. I don't think I need to do that right away. The first and foremost thing, yes, we need to do is basically parse our input, right? So, and for that purpose, let's say parse the grid. Okay, let's say what parse grid should look like. We know that we would receive an array of strings, let's say, right? That will be the input, let's say, and we should parse that and then form our grid. Okay, that's what we want to do. So let's say this array is GS, and okay, the obvious thing is the fact that we can, so each string, by the way, would essentially be the row, right? And so, and within that row, each character would represent the each position value or the point value, and then for the point value we will get, let me call this position. I think I like calling it position rather than, I mean, it's a minor thing, but yeah, okay. So yeah, so for each position, for that we can essentially call parse state to parse it, right? So which means we definitely have to map through GS, right? And that, when we map through GS, which is our grid string, which is an array of strings, essentially we'll be looking at each string, right? When we're operating on the function which maps takes, right? So we will get each string as input. So for each string, essentially we'll have to go ahead and do another map operation for parse state. And once we do that, once we call map parse state, now this will automatically give us a two-dimensional grid, I think. Yes, this is right. And like the HLint says, we can do an eta reduction. We can remove we can do a nice simple eta reduction. Now that we know how to parse our grid, let's improve our main function as well. So rather than splitting by words, let's instead just use lines to get all of the stuff, right? And so this should fix it. Yeah, and then we'll figure out what to do with it. So now that we have the grid, yeah, we'll have to come up with the logic for applying our rules. And so for that purpose, the first, I think the first thing that I would like to do is basically compute, or have a function that gives me a list of all the adjacent or the neighboring state values. I think, yeah, let's see what that would look like. So we'll call it adjacent states, let's say, right? And so this, let this receive a grid as an input, and we will give it a position as the second input because we want the neighbor for that specific position value. Okay, and for that, then we will, let's return a list of states, right? And let this be a linear list. We don't need a two-dimensional list, obviously. So let's, for the time being, say this is sorry, undefined, right? Okay. Another thing that I think will come in handy would be having a function such as inside grid, okay, which would take grid as input and position as input, and then it would return a boolean value stating whether this input position does it exist inside the grid or not. Yeah, I think having something like that would help me make sure that I can basically avoid or skip trying to process entities that are outside the bounds of the grid, right? Okay, so let's say grid, let's say pose. In fact, let's destructure this guy. So you can see some the row essentially would be this, and the individual state then would be this. Now I am, no, no, sorry. What we need to do here is ensure that x must be greater than equals to 0, and x must be, oh, it should be, oh, let's it should be less than max x, and similarly for y it should be greater than equal to 0, and y should be less than max y. And now our max x would be length of our grid. No, it would be length of head of our grid, and max y would be length grid. This looks nice. Now once we have this would help us for computing the adjacent states fairly easily now. So we have our grid, then we have the position. Do we want to break it down? Let's see, x and y, and for this now we want to save all the adjacent cells. Okay, let's first have this. Let me have a function that just gives me all positions, adjacent positions. Given a position, it should give me all adjacent positions, and it would look like, so if we have position x and y, this would then simply be so first would be x minus 1, and y. Okay, let's say y minus 1. So the leftmost, the next would be x, and again y minus 1. Then we would be x plus 1, y y minus 1, right? Then we will have position x minus 1, y, position x and y. No, we don't want x and y because we don't want to process the thing itself, right? And then we move on to the next row. So x minus 1, y plus 1, and position x uh, x y plus 1, position x plus 1, y plus 1. So these are all our positions, isn't it? Yes. So these are all the positions. Okay. Given okay, so given this, we would need a function such as state at position. So given a grid, given a position, we should be able to return what state it is in right now. We want to be able to look at that, obviously. And so this would be, we take, and then we take those x, y, and where the row would be grid y, and state would actually just be row x, right? Yes, I think so. Yeah, given a position, this would be, so now obviously I am assuming that the position we supply to this function should be within the bounds of the thing, which I think is an okay assumption. In a probably in a real world application, we probably would maybe not want to assume that, and make sure that our solution is capable of dealing with those exceptional circumstances as well. Where and in those circumstances we can typically either utilize something like a maybe monad, because maybe, so saying okay, if the position doesn't exist, it's nothing. Or we could even utilize an either monad and either data type, which would allow us to say okay, if it does exist, then the right of it would have a value, but if it does not exist, we may have some sort of, let's say, an error statement for as a left value for it. That's typically what we do. But here I think, at least for now, right, because I want to solve the problem in a sane amount of time, let's for now, let's do it this way. Now that we know what state is at a given position, we know what are the adjacent positions given a position. Mm, let's now say uh, we'll take all the adjacent positions. So where APS is adjacent positions of pose, right? This gives me all the positions. Then for that, I can so I can say, so these are all the adjacent positions for the given position, right? However, it is possible, because here I'm only doing math, right? So it is possible that some of these positions may be invalid positions. What we can do is, let's just filter out uh, only the valid ones, and the valid ones would be the ones that are inside the grid, right? Right. So let's see. I think this should be fine, right? Yes. So we filter and get only the adjacent neighbors who are inside the grid. Right. However, this is only giving us positions, right? This is only giving us positions. So what we would want to do is we can map state at pose through APS. And this, oh no, Stated pose also needs the grid. We can do this, and this would basically give us all the state values on those adjacent positions. The other thing, obviously important, is to sort of be able to count the number of occupied seats, because our logic is essentially based on that. So let's have a function, let's say count occupied, okay, or no, let's say occupied length. Is that appropriate? I guess it's fine. And so we will take a list of states and we will then return an integer here. I think it should be fine. So then we will say, so all the states can either be floor, empty, or occupied. So we'll just do a fold where we only count the occupied ones, or we can filter and length. So fold L F0, okay, where F receives an accumulator and it will return a state. Right. So for that, let's say, okay, if the state is occupied, then we will say occupied plus 1. Otherwise, basis. I think so. Yeah. Only if the seat is occupied do we actually count. Otherwise, it'll just be 0. I mean, it'll just, yeah, we won't count them. Okay. So we have the adjacent states, we have the occupied length. Now let's try and see how we can apply the rules, I guess. So let's literally call it apply rules. Now this obviously will receive a grid, and I should return the, yeah, I should return the next grid, which would be a grid resulting from the application of the rules as per the given problem. And just to it, let's look at it again. If a seat is empty, there are no occupied seats adjacent to it, then it becomes occupied. So we have these conditions. Okay. So essentially we have to traverse the entire two-dimensional array. We have to go from each position, and for each position value we have to count the number of occupied seats in all of the adjacent seats for it, right? And then based on that, uh, we would be deciding what the next state should be. Right. Let's first then have a maybe a subset of this. Let's say instead of the entire grid, let's look at one entity. Okay. Let's say we're given a, okay, we're given a state, we're given a position. This should give us the next state. Maybe this. So we have apply rule, state and pose. Right. Now we will get all the adjacent positions for pose, right? Yes. Oh, let's get the adjacent states. And this needs, oh, this needs the grid though. Let me think. So let's say, okay, let's receive the grid. Okay. Let's say we do have the grid and we have the position. Okay. Okay. And then this, we should then be able to say what the next state should be. Okay. Okay, let's think of it this way then. Now, okay. Now we can say, okay, the state would be state at pose grid pose, right? And let's say the occupied count would be occupied length of adjacent states of this. Okay, now let's say we have this, the next state, but the next state still depends on the current state. We have the state, right? So okay, let me then have a small helper function just to avoid some unnecessary complexity, saying so given, let's say we have the state, and because it depends on the count, let's say we will receive the state, current state, and the count of the this thing, and then based on this we have to essentially say, okay, what the next state should be. So I don't know, let's call it next state, I guess. So we receive a state, we will receive the integer, which is, and then we will use that to produce our next state. So next state of floor, again, does not depend, it will always be floor. Next state of empty. Now empty, it says, okay, if there are no occupied seats adjacent to it, 0, then we will become occupied, right? Now however, if it's empty but it's not 0, and basically it can be anything else, then it will remain empty, right? Okay, and finally for occupied, oops, so for occupied, the condition is 4 or more seats adjacent to it are also occupied. Then so for this, let's say n, we'll say if n 4 or more, right? So greater than equal to 4. So if there's 4 or more, then we become empty. Otherwise, it will remain occupied. The next state looks good. Okay. Okay, let's say, yeah, okay. So now for our applying the rule, all we say is we next state of state, and that's it. Yeah. So this gives us this applies the rule basically for one position. And in order for us to do it for the entire grid, basically we'll have to go through all the positions and keep applying the rule for each one of them. Yeah. So apply rules takes a grid. Let's say it's undefined. Now let's think a little bit. I want to think a little bit. So we already have the grid, so we can apply the rule, but we also need the position, which means, but then, yeah, we want the position of all of them. Okay, in order for us to get the position for all, we can obviously use list comprehension for that. Now let first get all the positions. Okay, so that would be we have pos x or y, where x would be coming from 0 to max x minus 1, and y would be coming from 0 to max y minus 1, right? This gives us all the positions except we need max x and max y. Let's do max y first, because max y would essentially be length of the grid. Max x would be length of head of grid. What is, yeah, okay, this is fine. Yeah, so we have all the positions, and then we have to use this to somehow get the, okay, so we basically can apply a rule for each of the positions, right? So we can again do map and then map apply rule for PS. Doesn't this work? But it's not just apply rule. We also need to say grid. So we know how to apply rules, and that gives us the next grid. Now coming back to the thing, what we have to do is we something is going to happen. The chaos stabilizes. So we have to keep applying until it stabilizes. Okay, apply rules until stable. Okay, what this will do is it takes a grid and return the final grid, I guess. So we have this, takes a grid, and so we will say, okay, if grid equals the next grid, then we just return the grid. Otherwise we will do something else where the next grid will simply be applying the rules for grid. Okay, okay. Spelling mistake. This says no instance of EQO. So our state for now cannot be compared. So that can be fixed easily by also deriving from the EQ class. So that will allow us to be able to compare them, and only unless we can compare the states can we actually compare the list of states. So yeah, okay. This already looks fine. Oh no, we have to look at what the otherwise mean should be. This should be just, oh yeah, this should be just apply rules until stable for the next grid. We basically just keep on doing it, isn't it? Okay. Looks interesting. So the first thing we need is say, okay, where grid is equals to parse grid of input. Let's say grid string. Okay. And once we have the grid, then we just apply rules till stable. And but not just this. We would, once we have the final grid, we want to count the number of occupied seats, right? So for that we could do something like, okay, sum, and we can say occupied. What is the occupied? Oh, it's the occupied length, right? So we can map occupied. Oh no, occupied length takes a list of state. Yeah, basically we receive the row, and so we apply the occupied length grid on the row. So it gives us it would give us the occupied length for each row, and then we just sum them up. Okay, so now let's look at what is wrong. It says expected can't match type state to int. Hmm, what's the oh no, that doesn't need the grid. Sorry. Oh, this is fine. Right. Let's look about this. It says 37. 37 is right. Let's run it against the test input quickly. 2289. It is actually slow. 2289. Yeah, it is right as well. So it is, but it is slow. Like I said, I think the one optimization for sure that we can do is back our data structure with the map, so that all our position lookups and stuff should become straightforward. I think that'll be all for today. Thanks a lot for watching. Please subscribe and share if you like the content. Thank you.